So today we're going to be talking about inverse trig functions. The last time you guys talked about these, you were in geometry. And what we're looking at here is, we'll actually look down at the examples first before we start talking about the graphs. What we're talking about here is when we write it like this, like sine with a little -1 right there. So this is not the same thing. Like sine inverse, that's how you say this, sine inverse. You could also say inverse sine. So the order doesn't matter. Or we can also call it arc sine. I don't actually know where that name comes from, but it means the same thing. This is not the same as 1 over sine. 1 over sine is like sine to the -1st power. And sine inverse, yeah, I know it has a -1 right there, but it's not raised to the -1st power. And so, yeah, I know this could be confusing because in different contexts, the -1 means different things, but that's why I'm telling you about it right now. Yes. This one over here is a cosecant. This is the reciprocal of sine. Sine inverse you want to think of as backwards sine. Welcome. Okay, so what we're doing when we see inverse sine is we're basically asking ourselves what angle on the unit circle, actually we're going to say what angle on the blank unit circle, I'll fill in the blank later, has this sine value or has this y coordinate. And there's a little bit of a twist to this, which is why there's a blank right there. But I'll tell you the twist in just a sec. So when we look at letter A, turn to your neighbor, what angles on the unit circle have a y coordinate of 1/2? Okay, so what angles have a sine of 1/2? Pi over 6. And? There's one other. No, that's -1/2. Five pi over 6. Yeah. Okay, so there's two angles on the unit circle that have a sine, a value of 1/2, pi over 6 and 5 pi over 6. The answer to this is just pi over 6. It's the one that you guys thought of first. I'll tell you why in a sec. Okay, so letter B. What angles on the unit circle have a y coordinate or a sine value of -√2/2? Turn to your neighbor. What are they? Okay, so what angles are we talking about here? 5 pi over 4 and 7 pi over 4. Okay, here's the twist. Neither one of those is the answer here. The answer is -pi over 4. I'll tell you why in a sec, but does -pi over 4, if we did the sine of that angle, guess, is it -√2/2? If we were doing the reverse problem of this, sine of -pi over 4, does that equal √2/2? Yes, it does. So even though that might not be the angle that we were thinking of, it does have the correct sine value. So I'll tell you why we're picking that in just a sec here. Inverse sine of root 3 over 2. What angle in the unit circle has, or angles, have a sine value of root 3 over 2? What angles are we talking about? What's that? Pi over 3 and 2 pi over 3. Yes. The answer to this is pi over 3. And last but not least, inverse sine of 0. Where does sine equal 0? Pi and 2 pi and 0. Our answer for this is 0. Okay. So, inverse sine is a function. Functions must have one output for each input. So when we plug a number into a function, we're supposed to get exactly 1. We could even put that there, exactly 1. So every time we do sine inverse of 1/2, we need to get the same answer every time. And so the same answer that we get every time is pi over 6. Even though there is another angle with a sine of 1/2, our output every time is going to be pi over 6. Same thing for all of these. There's more than one angle that has these sine values, that has these y coordinates. But because sine inverse is a function, we need to have the exact same output every time. This is also the same thing as passing the vertical line test. This is what makes it a function. So what goes in this blank here is the word restricted. We have a restricted unit circle for our inverse functions so that these things are functions having exactly one output for each input. The restricted unit circle, yeah, I'll just draw it down here, for sine inverse looks like this. I really wish that spell check would go away. So this is the unit circle that we're working with. Notice it goes from negative pi over 2 to positive pi over 2. We have our normal first quadrant here, pi over 6, pi over 4, pi over 3. And we have the negative first quadrant angles right here. So it's different than the unit circle that we're used to working with. But this is the one that we need to think of when we're doing sine inverse. It's also the one that we need to think of when we're doing cosecant inverse and tangent inverse. And so this is going to help us answer this question right here. Explain why sine inverse of sine of pi over 6 is pi over 6 is true, but sine inverse of sine of pi over 6 equals 5 pi over 6 is not true. So let's work inside out here. What is sine of pi over 6? One half. Oops. So now when I think of my restricted unit circle, which is right there, which of those angles has a y-coordinate of 1/2? Pi over 6. Okay. When we do the other one, what's sine of 5 pi over 6? Sine of 5 pi over 6 is? Yep. Now, when we do sine inverse of 1/2, well, we just did it. What does sine inverse of 1/2 equal? Pi over 6. Okay, the reason that this is not true is because this is not on the restricted unit circle. Okay, so let's see why this is true. Okay, here's our function here, y equals sine x. And let me just make sure we're in radian mode. We are. Okay. So here we see like our x-intercept right there is roughly 3.14. Can we be more exact with what that value is? Pi. And then over here, well, it's giving it away. Our other 0 is at 2 pi, which is like 6.28. Okay, so we wouldn't label the axis like this, right? We would label it with pi and 2 pi and 3 pi over 2 and pi over 2. But this is our graph of sine of x. Okay, so think back to algebra 1 and algebra 2. If we're doing an inverse of a function, what does that mean that we do? What does an inverse of a function mean? Shelby?
Change y and x.
Yes, that's exactly right. So we take y and x and we switch them. So if instead we graph x equals sine y, now our graph is going vertical instead. Now, as we look at this, kind of already mentioned it, what is the problem with this graph right here? It's not a function. So actually it's a function of y. If you turn your head sideways, like it is a function. But as we're looking at it this way, normal ways, this is failing the vertical line test. And so what we have to do is we have to restrict our graph, and we're restricting our graph to just this part right there. So I'm going to graph y equals sine inverse of x. And if you see the blue graph right there, it's overlapping, and I'll just turn off my red graph here so we can see it more clearly. That is what the graph of sine inverse of x looks like. Because this graph does not fail the vertical line test. This graph stops right here before it turns around and fails the vertical line test. And it stops right here before it turns around and fails the vertical line test. And so this is where our restricted unit circle comes from. This y-coordinate right there is negative pi over 2. And this y-coordinate right there is pi over 2. And so that's where we get our restricted circle. So we're going to draw that on our notes here. So you guys can do this too. Just graph your sine graph here. And if you have two different colors, once you graph your x equals sine y, if you want to just highlight here from negative pi over 2 to pi over 2, that is the restricted part of the graph. And if you were just going to do the restricted graph, it would be here. 1, negative 1, this would go pi over 2, negative pi over 2. Sort of like that. Okay, so that's why we're picking from a different part of the unit circle. And so what we have to remember is which part of the unit circle we're drawing from. So with cosine inverse, it's the same idea. When we graph y equals cosine of x, we can do our graph right now. Cosine has that mustache shape. Okay, so I've got my graph here of x equals cosine y. It has the same problem where we're failing the vertical line test. So we need to restrict this graph. Is it going to work to restrict this graph from negative pi over 2 to pi over 2? No, that's not going to work. Okay, so what should we pick instead?
Pi to negative pi.
Pi to negative pi? Yeah, good idea. What should we pick? What would be some good numbers to pick? Negative pi to 0. Would that work to make this a function? Yeah, it would. I would argue those aren't the best numbers that we could pick. Probably the second best. Huh? Pi to 0. Yeah, or 0 to pi. Yeah. If we pick 0 to pi, that those are nice, great trigonometry numbers. 0 and pi. And we can see it's not going to fail the vertical line test. So that is our restricted region for cosine inverse. It goes from 0 to pi instead. Which means we also use a restricted unit circle that corresponds going from 0 to pi. So the nice thing about this one is that it's just the good old unit circle that we know and love, just the top half. So pi over 6, pi over 4, pi over 3, and all of these angles are the same too. Now this is the restricted unit circle for cosine inverse and secant inverse and cotangent inverse. So that's a nice thing. There's 6 trig functions, but there's only 2 restricted unit circles that you got to keep track of. One's the top half and one's the right half. So, doing the same process that we did before, I want you guys to do these examples A through D. Ready, set, go. Okay, so where's cosine equal 1/2? Where's cosine equal 0? Where's cosine equal negative root 3 over 2? And where's cosine equal negative root 2 over 2? Okay, so for all those we have to choose angles that are from that part of the unit circle. Okay. Inverse tangent works the same way. If we graph tangent, we'll just do a sketch here. Here's our tangent parent graph. And so if we graph, I'm just going to do y equals tangent inverse. We can tell if we flip this graph sideways, we're going to fail the vertical line test because we have an infinite number of these tangent shapes, right? Like that those things are going to get in the way. So our restricted tangent function is just that middle part graphed like that. And since those vertical asymptotes are at pi over 2 and negative pi over 2, that's where our horizontal asymptotes end up when we flip it sideways. Okay, I'm going to change letter B right there to be tangent inverse of -1. So same idea. You guys do examples A through D. Ready, set, go. Okay, so where does tangent equal 1? What angle has a tangent of 1? 5, 4. Where would tangent be -1 on the restricted circle? Yep. Where's tangent equal √3/3? Pi/6. Yep. So remember our tangent trick. 3 + 3 is 6. Where would tangent be -√3? Yeah, -pi/3, exactly. Okay, so this is the same restricted circle that sine is working with. The way that I keep track of which functions use which circle, so the 3 of them that use this one are sine inverse, cosecant inverse. Does it make sense that those two are using the same circle? Yeah, those are reciprocals of each other. Tangent, when we split it up, what function is on top? Sine. Yeah, tangent is sine over cosine. So think of like sine is on top. It's going to use sine's circle. That's how I remember it. For this one, cosine and secant, of course, they go together. They're reciprocals of each other. Cotangent is written as what over what? Cosine over sine, yeah. So since cosine's on top, we're going to use cosine's circle. It's just a way to remember which function is which. Okay, so here's a summary of all of these graphs. So there's our sine inverse. Notice here it's called arc sine. Those are going to be used interchangeably. Arc sine is the same as sine inverse. We also have arc cosine, and arc tangent. And then if we look at our other groups, we didn't graph these, but this is what those graphs look like. So arc cosecant, arc secant, and arc cotangent. You don't need to be able to graph these. The purpose of the graph is to understand why those functions are restricted, why they have restricted outputs. So draw a line right here after 7, 8, and 9. So ignore those directions at the top right now. So as we're looking at these, what I would recommend you always do is graph a little sketch of both circles and just label like sine inverse, cosine inverse. And label this one -pi/2 to pi/2. Label that one 0 to pi, just so it can help keep you straight. If you also want to throw on cosecant inverse and tangent inverse, that's good. Nothing wrong with doing this every time. And so we just have to think, we have to restrict our thinking to those restricted unit circles, and our answers should only be angles from those unit circles right there. But notice, in order to do this, you have to actually know the regular unit circle pretty well, right? So That's why we warmed up with it and why we still need to know it. I'm going to have you guys do these 9 problems here. For 7, 8, and 9, just work inside out. So evaluate the inside first and then do the outside function. So take, I don't know, 2 minutes to do that. Ready, set, go. Okay, let's check. So arc cosine root 2 over 2 is pi over 4. This one's negative pi over 4. This one's pi over 3. Okay. Cosecant equaling 2 means that sine is 1/2. They're reciprocals. So that's pi over 6. Secant equaling negative root 2 is the same as cosine equaling negative root 2 over 2. So that's 5 pi over 4. Cotangent equaling negative 1 is 3 pi over 4.
Why is it pi over 6?
This is the same as sine of theta equaling 1/2. 2 is the reciprocal of 1/2. So for each of these, as I do arc cosine, I have to think, okay, that is the circle I'm looking at. Arc sine, that one, arc tan, cotangent inverse, secant inverse, cosecant inverse. We got to make sure we're thinking of the right part of the circle. For these, sine of 1/2, arc sine of 1/2 is pi over 6, so we just do cosine of pi over 6, which is root 3 over 2. Cosine inverse of negative root 3 over 2 would be 5 pi over 6. Cosine of 5 pi over 6 is negative root 3 over 2. Arc sine of 0 is 0. Tangent of 0 is 0. Okay, so if you don't know your unit circle, it's going to be tough. But you got to know it. Well, let's look at these examples right here. What do you notice about these numbers inside here? Yeah, these are not unit circle numbers. Okay, here's what we have to do. We have to draw the triangle that goes with these numbers in the right quadrant. So, for arc cosine of 3 over 5, first of all, we're thinking cosine inverse is those two. Which one of those two quadrants is cosine positive in? First or second? First. So we draw our triangle. And what this is telling us is that the cosine is 3 over 5. Looks like a B. So that means my adjacent is 3, my hypotenuse is 5, or my x and r, 3 and 5. So then what we do is we take the sine of this angle right here. What would the sine be? 4 over 5. Yes. So what do we have to do, what's the middle step that we skipped over? Yeah. Yeah, just find the missing side right there. Exactly. If we saw, for example, number 13, this is cotangent inverse. Which quadrant should I draw this triangle in if it's negative? The second quadrant. Because cotangent inverse comes from those two right there. So I draw my triangle there in the second quadrant. Cotangent, I need to remember, is x over y. So this is 3 and that's 2. And which one of those should be negative? The 3. I'm trying to do the cosecant of this angle. So I need to find the hypotenuse. So I am going to need to do Pythagorean theorem. So I'm getting 4. Should this be 4 minus 9? Yeah. When we square a negative number, it's always positive. 13. So our hypotenuse there is root 13. So now when I do cosecant, what do we get? Yeah.
Root 13 over 2.
Yep. Okay. So that's the process. When our numbers there are not from the unit circle, we have to draw the triangle and figure it out. You guys do 11, 12, and 15. Ready, set, go. Okay, let's check these. For number 11, what quadrant are we drawing this triangle in?
Yeah.
First. Yes, so 3 over 4. Is the other leg 5?
No.
No, it is not. What is it? Root 7. Okay. Now, do we actually need to find the other leg in order to answer this question? We don't. So we could just notice that we already have the legs that we need, but in general, you usually will need to find it, but not always. That'll be 4 over 3. What quadrant are we drawing number 12 in? Also first, yeah. So if the angle's positive, it goes in the first quadrant. Sine is 2 over 3. If we're doing tangent, we do need that other leg. What does the other leg equal? Root 5. So tangent would equal, yeah, 2 over root 5, which when we rationalize it is. Nice. Okay, where's the triangle go for 15? Yeah, second quadrant. So again, for secant, inverse, you want to use that part of the circle.
But I thought we would draw the triangle if it's not on the unit circle.
Yeah,
3 over 4 not on.
3 over 4 is not in the unit circle. So you don't get it confused with 3 pi over 4, which is an angle in the unit circle. Remember, these numbers represent like the x coordinate or the y coordinates, or both. Yeah. So 13 and 5, which of those should be negative? The 5. Remember, the hypotenuse is always positive. What is our tangent value here? Yeah. So just go ahead and memorize 5, 12, 13 if you haven't already. Okay, so that's how we do those.
Why are we not doing 14?
This 1/2 in there is going to change things. Yeah. That's using a half angle identity, which we didn't learn this year, so we don't need to do it. Okay. So that's it for our notes.